In this video, we're going to learn about the ozone layer, and we'll learn about the bond energies between ozone and oxygen, and begin to understand how the ozone layer is formed based on these bond energies and UV radiation. So first of all, we need to take some time to talk about what makes Earth so special. So Earth is unique amongst the planets in our solar system because of its oxygen-rich atmosphere. And oxygen exists in two different forms, O2 and O3, which are seen below here. So oxygen, O2, has a double bond between the two oxygen atoms and then two lone pairs of electrons on each oxygen atom. Ozone is a little different, and we're going to talk a little bit more about its structure in the next bit. So what makes ozone so special? Well, first of all, the word ozone comes from the Greek word to smell. Ozone actually has a distinctive smell. After a lightning storm, sometimes when you go outside, the air has this distinct, crisp smell. That actually is ozone that you're smelling. Ozone is much more unstable than oxygen. It has a lower bond energy, so it's more easily broken apart. And oxygen has a pair of delocalized electrons, which then gets shared between the two single bonds. So this gives the molecule resonance. So sometimes the delocalized pair of electrons will move to here, which then will cause this double bond to move to there, and then sometimes it goes back the other way, so the molecule has resonance. Now, ground level ozone is harmful to humans. There are a few ways it can be made. It can be made when electricity passes through oxygen, so like in an electrical storm, or when nitrogen oxides and organic oxides are released from cars and industry. So we really don't want to have a lot of ground level ozone because it is dangerous. However, atmospheric ozone, along with oxygen, absorbs UVC and UVB radiation, protecting Earth from those harmful rays. So UVA radiation can come through, and some UVB gets through, but almost all of the UVC is absorbed by the ozone in the ozone layer. So where did our Earth's oxygen come from? The early atmosphere was actually oxygen poor, but atmospheric oxygen levels began to increase with the arrival of photosynthetic organisms like plants, cyanobacteria, algae, and so on. So this ultimately led to the development of our protective UV-absorbing ozone layer. So the purpose of the ozone layer is to absorb almost all of the UVC, 95% of the UVB, and then only about 5% of the UVA is absorbed. But that's okay because UVA is required to activate the production of vitamin D. And without vitamin D, we would have lots of problems with our bone structure. So in the atmosphere, 90% of the atmosphere's ozone is found in the lower part of the stratosphere, and that region is called the ozone layer. It has a concentration of less than 10 parts per million. Oxygen is in dynamic equilibrium with ozone, and they're continually being destroyed and reformed in a cycle. And we'll take a look at those formations and destructions in the next few moments. So first of all, we'll take a quick look at the bond energies of both oxygen and ozone. Oxygen's bond energy is 498 kilojoules per mole, and ozone's is only 364. So the thing that dissociates oxygen is UVC, and it's dissociated by wavelengths of less than 242 nanometers. And then ozone, with its bond energy of 364 kilojoules per mole, is dissociated by UVB with a wavelength of less than 330 nanometers. So UVC, with a wavelength of 200 to 290 nanometers, can break apart oxygen, and it produces two oxygen atoms, or radicals. And these free radicals are highly reactive, and they'll find something to react with. These free radicals will combine with oxygen to form ozone, so another oxygen molecule. And ozone prevents UVC from passing beyond the stratosphere. So this absorption of UVC warms the stratosphere when the norm would be a decrease in the temperature with rising altitude. UVB breaks ozone into oxygen and an oxygen radical. The bonds in ozone are weaker than oxygen, which is why the lower energy UVB can break O3's bonds. And this cycle of breaking and reforming oxygen and ozone explains why UVC and UVB are absorbed in the stratosphere. So the UVC is stopped by oxygen, and then that allows the formation of the ozone, which will then stop the UVB. So it's probably important that we take some time to talk about chlorofluorocarbons, or CFCs. They were actually once thought to be safer choices for refrigerants and aerosol propellants. And the reasons being were that they were chemically unreactive at ground level, they were biologically unreactive, so they didn't hurt us, and they could be liquefied at pressures just above atmospheric pressure, so you didn't have to put them under high pressure, which can be a danger if heated up, because high pressure things could explode. So it seemed like a win-win-win situation. They were also safer for us. They were safer to handle than ammonia, even though they were more expensive, but they decided to use them because of their safety. However, in the 1970s, scientists discovered that chlorofluorocarbons were destroying the ozone layer. In the stratosphere, they get broken down by sunlight and they create free radicals. So you take a look here, breaks off one of the chlorine atoms and creates a free radical, and that free radical reacts with ozone to make another free radical and oxygen, and it just keeps going on and on. So it's not good. By 1985, scientists had discovered the ozone hole over the Antarctica. This led to global agreements to be signed in Montreal in 1989 and in London in 1990 to ban or drastically halt the use of chlorofluorocarbons. And it's been many decades, but by 2016 it became evident that the ozone hole is beginning to repair itself, even though it will take quite some time, many decades still, to completely repair itself.